Hi everybody, welcome to another video in linear algebra, section 1.5, solution set of linear system. What we learned so far is that a system of equation can be written in different forms, a metric matrix, vector form, or the matrix form. And to solve for it, up to this point, only one way is to use Gauss-Jordan elimination to turn a metric matrix into the reduced row echelon form. Now, when we do the row operation, what we do is just the interaction between the entry into in a column. So, for example, if we want to eliminate these three, we do the multiply -3 into the first row and then add to the second row, and we do that for each element. And each entry will interact with each other within the column. In that case, in this particular example, we might have something else other than 5, 2, and 5. It could be anything. The first part is still going to be the same, right? If I have different number than 5, 2, and 5, I may have different numbers here on the last column, but the first three is still going to be the same. And that's what we focus here on the next on this section. Right, homogeneous linear system. A system of linear equation is said to be homogeneous if it can be written in the form x equal to 0. 0 here is the vector, and vector in Rm. Such a system always has at least one solution, namely the vector x equal to 0 vector. This 0 vector is in Rn, and the solution equal to 0 is called the trivial solution, the obvious solution. The homogeneous equation has a non-trivial solution if and only if the equation has at least one free variable. We'll talk about that later. But let's look at an example here. I just write consider this. So we have the system. I write that in the matrix form. A, B, C, D, E, F. Right. We multiply by, just use pencil, x1, x2, and x3. So when we multiply like that, it is going to be equal to a 0. Remember, the result vector on the right hand side have to be the same dimension as each column vector in the matrix. So this is a two-dimensional vector. We have two-dimensional vector at the end. So that's what the Rm means. Now, the trivial solution is when we have all the 0 here. If we have 0 here, here, and there, this is a trivial solution because anything times 0 is 0, right? And notice that this x0 is the trivial solution. The solution itself and the last column might not have the same dimension. That depends on what we have on the matrix. So I draw this example just to demonstrate that the dimension of this 0 vector and the dimension of the trivial solution 0 vector may not be the same. Right. Now, the homogeneous equation has a non-trivial solution if and only if the equation has at least one free variable. We'll see that in a minute. Right. Now, determine if the homogeneous system has a non-trivial solution and describe the solution set. So, I said up to this point, one way we solve the equation is to put in the augmented matrix reduced row echelon form. After that, 1, 2, 0, 3, 4, and 0. And we apply reduced row echelon form or Gauss-Jordan elimination process. this, of course, we can just do by hand, but just going to put that in the calculator. So 2 rows, 3 columns. 1, 2, 3, and 4. So we have that 1, 0, 0, and 1. And we still have the augmented matrix. Right, so we have the system equation, the right hand side 0, so this is homogeneous system, and when we do the reduced row echelon form, we have this. And notice that when we write the augmented matrix, we can say this column is for the x variable, this column is for the y variable. And finally, we have the pivot on the x column, pivot on the y column. So x and y, both of them are basic variables. So there's no free variables, and the solution x equal to 0, y equal to 0. And this is the trivial solution. Or if we want to write the solution, we can say the vector x is equal to a 0 vector. Yeah, either we write like that, or we write in the vector form. Vector x equal to 0 vector. As you see, this one we have no free variable. All the variables are basic. So in that case, we only have trivial solution. So, no free variable. So in that case, we only have only trivial solution. And of course that is trivial solution. Right. Simple enough. Now look at another example. Once again, I'm going to put that in the augmented matrix and then find the reduced row echelon form for it. Right. By the way, on this problem, just save the other half of the page. Yeah, I want to write reserve the half of this page for something else later. Right. Reduce row echelon form. 3 by 4. Right. We don't really need to put 3 by 4. We just put 3 by 3 because the bottom, the last column is 0. Doesn't matter what we do, it's still 0 at the end, right? We only need to put that, and operations, we still have 0 at the end, regardless of the operation that we do. Right. So here 3, 5, -4, -3, -2, 4, 6, 6, 1, -8. Right. Mentioned before, all the row operation, we just multiply and add or subtract. The answer should be able to be written in fraction. So that is what we have. So I'm going to write that down. Right. 1, 0, negative 4 over 3, 0, 0, 1, 0, 0, and the row 0. So once again, corresponding to the variables for each column. Right, now we have the basic, we have the pivot for x1, for x2, so those variables are basic. There's no pivot on the column x3, so in that case we say there's a free variable, so we just say there's nothing here, so we say x3 is free, x3 is a free variable. And then knowing the top two equation, we can rewrite this as the equation 1x1 minus 4/3 x3 equal to 0. And then we have x2 equal to 0. And x3 is a free variable, so we can choose anything. Because there is a free variable, this one has a non-trivial solution. So there's a free variable here, so non-trivial solution. If there's a free variable, there's a non-trivial solution. x1, if we move the 4/3 x3 on the other side, so we have x1 equal to 4/3 of x3, x2 is equal to 0, and x3 is arbitrary because it's free, so x3 can be anything. Or if we write this as a vector form, the vector x that has three components, x1, x2, and x3. X1 is 4/3, x3, x2 is 0, and x3 is arbitrary, so we just say x3, just x3. Right. So that is a non-trivial solution. Right. Like I said, we'll get back to this. And let's go to another example. Right. So once again, yeah, just for the page in half, we're going to knit the other half later. So first, we write this equation, just one equation, still can write that as an augmented matrix. Right, and then we still do reduced row echelon form. Or we don't even need to do that. But pretty much we divide everything by 10. That is the only operation we can do. Just don't need to do that. If we do, we'll have divide everything by 10. 1 minus 3 over 10. Negative 2 over 10 is negative 1/5. And 0. Right. Of course, if we want to, we can add a few rows of 0, so it has better for the matrix like 3 by 4. I can add 2 rows of 0, but I don't need to. Here, once again, corresponding to the first column is x1, x2, and x3. And we see here, we only have one pivot, and that is on x1. So in this case, we say x2 and x3 are free. x2 and x3 are free variable because they don't have pivot on that column. Right, and we can rewrite the equation as x1 minus 310, x2 minus 1/5, x3 equal to 0. Right? And now we write the solution. Because there's 3 variables, so there will be a non-trivial solution. Should be solutions, because when we write like this, x3 can be anything, so that is infinitely many solutions, so we could say solutions. Anyway, so we can solve for x1, move this to the other side, so we have the system, the solution will be x1 equal to 310 x2 plus 1/5 x3. X2 can be anything, and x3 can be anything. Right, we can write like that. Or if we want to write this as a matrix form, we have 3 components, x1, x2, and x3. X1 will be 3/10, x2 plus 1/5, x3. x2 and x3 are arbitrary, so we just say x2 and x3 will be x2, x3 equal to x3. We can choose anything for x2 and x3. Once again, we'll get back to this in a minute. Right, now parametric vector forms are there. The equation of the form of x equal to s times u plus t times v, u and v are vectors, and s and t are real numbers. This is called a parametric vector equation of a plane. So seen here we have 2 vectors, it's going to be a plane. Remember the sample that I used previous section. If we have 2 vectors that are not multiple of each other, we will have the whole plane. Right? To control a remote control car to go on a plane, we need a button that make the car move backward and forward, and one to move left and right. Right? So a plane, 2-dimensional object, we're going to need 2 vectors. Whereas the equation x equal to tv, this is 1 vector. We have 1-dimensional object, which is a line. And whenever the solution set is described with the vectors, we say that the solution is in parametric vector form. So we can write like this as a parametric vector form, but we can write even better. Now this go back to the sample that we have earlier, and that's where we have half a page there. Now we have the solution as this. Now if we continue as the solution. We have x equal to 4/3 x3 0 and x3, right? we can factor out x3 out of the matrix. B4 over 3, 0, and 1. Right? In this case, we write like that, and we say x3 is any real numbers. We can also write this simple. x3 is in the set of all real numbers. Just spell it out. Yeah. So that's what this means. So we write the solution x in terms of arbitrary number times a vector. So since the solution is given by only one vector, so the equation describes a line. So we say the solution, and of course what we did here, we need to describe the solution. So this is the solution is a line, and a line that characterized by within this direction. Right. Since we are here, we only have trivial solution, so the solution is 0, 0. It's just a point at 0, 0. But anyway, if we have the solution given by one vector, that is a line. Right. Of course, as you say, the solution given by one vector, of course, only one parameter. So this represents a line. Now, this solution we have here, let's rewrite as the parametric form. So we have x equal to, now notice the way I write this, 3 over 10 x2 plus 1/5 x3. Now I try to align the variable 3, 10 x2 and 1/5 x3, and I'm going to put x2 in here to align with x2, and put x3 here to align with x3. Of course, I can put 0 there and 0 here. After that, I can split this in two. We have 310 x2, and then there's x2, and there's nothing here. So I split that vector into two. 1/5 x3, 0 x3. Right? So the solution give like this: align all the x2 together, align all the x3 together. That's what we have. And then we factor out the x2. Have 3 over 10, 1, and 0. And then we have x3. Factor out, we have 1/5. There's nothing. There's 1. And so that is the solution, where x2 and x3 are arbitrary. So just x2 and x3 in the set of real number. So as you see in this problem, the solution will have two parameters, x2 and x3. So since it have two parameters, and of course represented by two vectors, this is a line. The solution is a plane. The plane will have two directions. Right. So if we have one parameters and one vector, that is a line. Two parameters and two vectors, it is a plane. Right? We have the picture here. 2 vectors, we have a plane. 1 vectors, we have a line. Right. Now more simple. Solution of non-homogeneous system. Now let's solve this equation. Matrix system, the matrix equation in that form, of course, we can just put in the matrix. Right, and then we just use the reduced row echelon form. Right, 3, 5, -4, 7, -3, -2, 4, and -1, 6, 1, 8, and -4. Right. So again, on this one, we don't know what are the variables. Just by default, let's just say x1, x2, and x3. So in this example, we have the pivots on every column on the left hand side. So x1 is basic, x2 is basic, x3 is basic, and the solution is x1 equal to -1, x2 equal to 2, x3 equal to 0, and -1, 2, and 0. That is the solution. So the solution is just a point in R3. So we say the solution is the point -1, 2, and 0 in three-dimensional space. Let's just go back, and this is 3 variables. So we just say the solution is a plane in R3. Yeah, just to make it complete. And also 3 variables here. So the equation is a line in R3. Yeah. So we have a line on 3-dimensional space and a plane on 2-dimensional space. Alright. Of course, no free variable here, no parameters. The number of parameters corresponding to the number of free variables that we have. Of course, here we have 2 free variables, 2 parameters. Right. Now, what we just did is a non-homogeneous system of equation because we don't have 0 at the last column. If we have only 0 at the last column, that is homogeneous system of equation. 0, like what we, if we have 0 at the last column, that homogeneous system of equation. Now we deal with the non-homogeneous system of equation, meaning we don't have 0 at the last column. Right. It says here, when a non-homogeneous linear system has many solutions, the general solution can be written in parametric form as one vector plus an arbitrary linear combination of vectors that satisfy the homogeneous system. Of course, you will see one example that we have more idea of what we have. Right, now it says that suppose we have the solution to that system is x equal to t V, and V is a homogeneous solution, then we have a particular solution equal to B. Then the solution of AX equal to B can be written as V plus P. So let's say we have a homogeneous system of equation is this. So this is homogeneous. System of equation, and the solution is this line, which characterized by this vector V. We can go in that direction, could be that much or the other direction, right? Now let's say we have the equation of AX plus B, which is non-homogeneous here. And the solution instead of this line, it's going to be this line. It would translate by the vector P. So we're going to have the solution as this line. Everything will shift in that direction. All the points will shift in that direction. And the same thing for a plane. I said it doesn't make a lot of sense, but when we do one example, you will see. Right, more theorem. And that's more or less is the same as what we have earlier. Suppose the equation is consistent, that means it has a solution of some given B, and let P be the solution. Then the solution AX plus B is a set of all the vectors of the form where V sub H is the homogeneous system of the equation AX equal to 0. Loosely speaking, if this has a solution, then the solution Z is obtained by this translate by vector P. We'll see. Now let's look at these two examples. One of them is a homogeneous equation because we have 0. The other one is not. So same thing, put in the matrix, reduce row echelon form. Augmented matrix. Reduce row echelon form, right? I can almost do this by hand, just multiply by 2 on the first row and add to the second row. This one we do have the variable, so we have x and y. Right. X is basic, y is free. So the solution, we can write this x1 plus 2x2 x plus 2y equal to 0. Sorry. So x plus 2y equal to 0. So the solution can be written as x. We move the 2y to the other side, negative 2y, and then y is arbitrary. Or if we write this as a parametric form, vector x equal to xy, where x is equal to negative 2y, and y is arbitrarily chosen, so it's still just y. Factor out the y, we have y times negative 2 and 1. Of course, the solution y is arbitrary, so we say y is any real numbers. Right, so that is the solution to the homogeneous system. Now, let's do that for this non-homogeneous system. Pretty much the same thing though. Write augmented matrix. Reduce row echelon form. Right, I just go back, highlight that, hit enter, that is copy and paste. Change 2, 3, and 6. So I have that. Sorry. Negative 6, right? Yeah, otherwise there would be no solution because we have the pivot on the last column. Right. Right. Now once again the variable we know is x and y. And we know x is basic, y 3. But we can rewrite that as x plus 2y. See, I write a little small, and I have to bring it closer to the camera. Right, better. And then so the solution will be at x equal to 3y negative 2y plus 3, and y is arbitrary. Or written in parametric form, vector x, two components x and y. First we have negative 2y plus 3, the other one is just y. Right, here you can split that in two, one with y and one without it. Right, sorry, have to erase the page number to make room for the solution. Right, so with that we can factor out y, and we have negative 2 and 1 plus 3 and 0. Right, so factor out y, we have negative 2 and 1 and 3 and 0. Now look at the solution of these two. We see that we have this component for the homogeneous solution. In that case, this 3 and 0 is called a particular solution. Right. So that's good and all now. Now let's look at the graph of this. I'll try to sketch the graph. Just a sketch. First of all, we have the vector negative 2 and 1, negative 2 on the x, and 1, negative 2 on the x, and 1 on the y. So this is negative 2 and 1. Right? And so the solution of the homogeneous system is the whole line. This is the solution to the homogeneous system, the whole line, generated by the vector -2 and 1. Now, the non-homogeneous solution, we're going to have the point 3 and 0, 1, 2, and 3, the point 3 and 0 here, and then we still have the vector -2 and 1. So the solution of the non-homogeneous system is going to be parallel to it, and that is the solution of non-homogeneous system. So we have homogeneous system, go to the point 0, 0, and we just shift to the point 3 and 0, we have a new line. By the way, the particular solution, in this case 3, is 3, the vector 3 and 0, it could be anything. We can pick any point to be a particular solution. We can pick this point as a particular solution. Any point on that line, we achieve the same thing, because we just need a point and the direction, so we have the line for the solution. Right, so homogeneous equation, we have the solution, and non-homogeneous solution, we should have the same part of the homogeneous and only different by a particular solution. And that particular solution can be anything. It could be 3 and 0, it could be 1 and 1 here, it could be 1 and 1. We just have different y values, right? Because that 1 and 1 is still on the line of the solution. Right. Now the way we write the solution, of course, use reduce the matrix into reduce row echelon form, and then write the basic solution as the in term of non-basic, basic variable in term of free variable. And after that, if we have 1 parameters, equation is a line. If we have 2 parameters, the equation is a plane. If we have no parameters, then it's just a point. Of course, we still can have no solution. And after that, when we have the solution, we're going to split in terms of homogeneous solution and particular solution. Of course, in this case, we still need to write y as any real number. Right. Let's do the same thing for this problem. Describe the solution or the intersection of these two planes, or pretty much just the solution of those systems. Just written differently. So we have equation of each one is a plane, and just find intersection. So put in the romantic matrix, reduce for echelon form. 1, 4, -5, and 0, 2, -1, and 8. Reduce row echelon form. Right. 1, 4, -5, 0, 2, -1, 8, 9. Right, so we have that. 1, 0, 3, and 4, 0, 1, -2, and -1. Right, now the variables x1, x2, x3, the pivot is here and here. So x1 and x2 are basic, x3 is free. It's a free variable. x1 and x2 are basic, and we write the equation. We'll have x1 plus 3x3 equal to 4, x2 minus 2, x3 equal to minus 1. Right? And then we solve for the basic variable x1 and x2 in terms of x3. So we can solve for x1, move everything to the other side. x1 equal to negative 3 x3 plus 4, and x2 equal to 2 x3 minus 1, and x3 is free, is arbitrary. Or we can write this as a vector. Negative 3x3 plus 4, 2x3 minus 1, and x3 is arbitrarily chosen, so just x3 could be anything, but just say x3. Now I'm going to split this in two. And there's nothing here, so just put 0 there. And then we can factor out x3. And then we have 4, negative 1, and 0. Right, so of course x3 is any real number. So what we have here, this is the solution. It has one parameter, so the equation is going to be a line in three-dimensional space, a line in R3, and that line will go through this point. This is a particular solution, and we'll go in that direction. So particular solution, it gives us a point on a line, and the vector goes with the parameters which determine the solution. I mean the direction of the vector. So I will say solution is a line in R3, and that line go through the point 4, negative 1, and 0. It's a line that goes through the point 4, negative 1, and 0, and will be in the direction of negative 3 and 2, 1, in direction of. Now I write the vector in the triangular bracket, negative 3, 2, and 1. I said the point, the vector, different notation, doesn't matter as long as they have 3 components. It could be in column. When we write the vector like what we use in Cal 2, Cal 3. That, yeah. Once again, particular solution give us where the line or the plane goes through, and vectors that go with the parameter give us the direction. Did we do this before? So write the general solution of this equation. Right. So once again, we start with the augmented matrix. And do the reduced row echelon form. This one is simple. To get this to 1, we just divide everything by 10. And the variables x1, x2, x3. The pivot is on x1. Right, so the solution will, of course, we can rewrite that equation as x1 minus 3 over 10 x2 plus 1 over 5 x3 equal to 7 over 10. And also we have x2 and x3 are free variables. Right. And of course we rewrite the solution as x1 equal to, I move all these two to the other side, 3 over 10 x2 plus 1/5 x3 plus 7 over 10. x2 is arbitrary. And x3 is arbitrary. Right? Or in the vector form. X1 just going to be that. X2 is arbitrary, so I put x2 here, x2 just x2, and x3 again arbitrary, so I put x3 here. Then we can split the vector. This is going to be the first one, and factor out. So we have x2, 3, 10, 1, and 0. And then the second one is going to be factor out x3. We have 1/5, 0, and 1. And the particular solution is just 7 over 10. 0, 0. And so we say x2, x3 in the set of real number. Right. So because we have two parameters, x2 and x3, this equation, the solution is going to be a line. I'm sorry. Two parameters, so the equation is going to be a plane. The plane that go through these two, I will go to this point, and the plane will contain the two vectors here and there. Of course, in Calc 3, if we want to find the normal vector to a plane, we do the cross product of these two vectors, but that's another story. Right, once again, we can write the equation augmented matrix, reduced row echelon form. From there, we can determine how many free variables that we have, too. So in that case, we have two parameters as the solution. So the solution is going to be a plane. Right. If we have one free variable, we're going to have one parameter, and the solution is going to be a line. Of course, relatively speaking, if we talk about R3, if we have x, y, z and more variable than 3, then we talk about 3, 4 higher than 3 dimension. But still, it's going to be a line in 4-dimensional space or a plane in 4-dimensional space. We cannot be able to visualize it, but at least we can write the solution. But anyway, that's the end of section 1.5. As always, thank you for watching, and see you in another video in linear algebra.